Calculus BC, our Chapter 7 review for our quiz. Let's keep going here and take a look at number 5. As we're looking at number 5 here, you can see that we've got f of x equals cosine of x to the x. Really, that's like y equals cosine of x to the x. We're supposed to not only take our derivative, but plug in a pi over 4. But really what we're going to need to do is take a natural log on both sides. The reason for that is we can bring down our x, and x is going to get multiplied to the natural log of the cosine of x. Please understand, we're not allowed to just drop the x down in the original form and then subtract a 1. That's only when x is raised to a positive real number, or a function is raised to a positive real number. If you had cosine of x to the 5th, of course you can bring that down. But here, whenever you have that x up there, it's going to require some special work. We're going to take our derivative right now. Derivative on the left is 1 over y, dy dx. The derivative on the right, we need the product rule. We'll have x multiplied to, well, the natural log of the cosine of x, we'll have to say 1 over the cosine of x. Multiply, chain rule here, derivative of cosine is negative sine of x. Then we'll say plus, then I'm going to take my derivative of x, which is 1, multiply that to the natural log of the cosine of x. Now, of course, right here, negative sine of x over cosine of x actually could become the negative cotangent of x. So I'm going to do a couple of things right now. I'm going to rewrite this over here, and in fact, I'm actually going to bring the y to the right-hand side, multiply both sides by y. But this right-hand side, like I said, it's really negative x cotangent of x. And then we could say plus natural log of the cosine of x. Now, one little added thing, that y right here is really what f of x is. It's the cosine of x to the x. So dy dx is cosine of x raised to the x power. And then inside here we've got negative x cotangent of x plus the natural log of the cotangent of x. Now, if all they wanted was our derivative, we'd be done. But they're really saying, by the way, please plug in a pi over 4. Now we know the cosine of pi over 4 is really radical 2 over 2. And that would be raised up to the pi over 4 power. Tangent of pi over 4 is 1. So the cotangent of pi over 4 is also going to get you a 1. So I have negative pi over 4 times a 1. That's just a negative pi over 4. The cosine here, I think I miscopied that. That's the cosine of x right in here. The cosine of x, when I plug in pi over 4, I'm going to get root 2 over 2. And that, as strange looking as it is going to be your final answer. Let's do number 6 also and take a look at that. We're trying to find y prime. We're trying to find dy dx. And the immediate observation that we can make is that we're actually dealing with a y on both sides. We're going to have to deal with implicit differentiation. Now, I'm going to do something that you don't have to do, but I do strongly suggest doing it because it's going to make your life easier. I'm going to exponentiate both sides. I know I'm going to have to deal with implicit differentiation at the end of the day, but this right here is going to greatly make our lives easier. I'll tell you why. Just previewing a little bit, even though I could have started by taking derivatives immediately, this present form is way, way easier. So I'm going to take my derivatives now. The derivative of e to the y is e to the y, but we're taking this implicitly. So we'll have a dy over dx. The derivative of 3x squared, again with respect to x, would be a 6x. The derivative of this minus 3y squared would be a minus 6y, but we're going to need a dy dx. Now, from here, we want to solve for dy dx, so I'm going to bring this 6y dy dx to the right-hand side. I want to get my dy dx's together. Then I'm going to factor out a dy dx. And hopefully you can see where we're going. It can look to be like it's a rather strange answer, but with implicit differentiation, it's perfectly okay to have answers with y in your derivative. And this would be legitimate and perfectly good. You could, of course, have done this problem originally just by taking the derivatives as they stand. Again, that would be just a little bit tougher.